Okay, so this is the first in a series of videos introducing the concept of runoff and hydrographs, which is chapter 8 in the Mays book. And so this follows up from chapter 7 where we're talking about the hydrologic cycle. So I wanted to find first what is a hydrograph. So all it is really is a relationship of flow rate versus time at a particular location on a stream channel or drainage element. So you can see an example hydrograph right here, time on the x-axis and flow rate on the y. And we're usually going to use these in response to storm events. So you can see in a dry period here at the beginning of the hydrograph we have base flow, which is that portion that's just draining to a river or creek when there's no rainfall runoff, just from groundwater. And then we have some rainfall. Sometimes this is plotted upside down actually at the top here in inches or millimeters. We have the rainfall. As a response, we start seeing some saturated overland flow. That's going to be the surface runoff. We also have some that's infiltrated into the unsaturated zone, and then that is actually flowing out into the stream flow. So you can see this interflow portion as well with time. But after the rainfall stops, a long enough period goes by that the runoff starts decreasing, and we eventually get back to the point where we just have base flow entering the creek again. So this is storm flow response, several parts: the base flow part, interflow, and then the saturated overland flow or surface runoff. This is showing the dry period, just the base flow, and then during the storm, the other portions as well. When we think about these hydrographs down here, you can see there's several other figures here. This one on the left is essentially showing the same thing we're just looking at. We have a total stream flow hydrograph, which we can break into portions. Here we have Horton overland flow, which I'll relate to Horton in a minute. The base flow portion, direct, or what we sometimes call incident precipitation, the precipitation that actually falls directly onto the surface of the water, and then the interflow portion, the flow from the unsaturated zone into the creek. Up here you can see two different rainfall events. These are rainfall hydrographs. Here's one, here's another, and then what the associated streamflow hydrograph might look like. In this case, the bulk of the precipitation was at the beginning of the storm, so we see it come up and then go down, whereas if the bulk of the precipitation is later in the storm, the peak of the hydrograph is shifted further back. A couple other things here. You can see these are watersheds with creeks running down them to the base of the watershed. And we're plotting on the right here the hydrograph for each of these two watersheds. So storm A is only in one small portion of the watershed. It drops its precipitation. It takes a while for that to work its way downstream to the outlet where we're plotting the flow rate. And so for storm A, which is right here, you can see it takes a while before the peak actually hits that point. And it's fairly low peak as well because there's only a small portion of the watershed in which the storm fell. Versus storm B, which takes up the whole watershed, immediately at the outlet you start seeing a response of the runoff from that storm event. So you see it come up right away, and then a much higher peak again because there's just a lot more volume of runoff occurring in the watershed. These both assume that the storm stops at some point, and thus we see the decline in the runoff. If the storm kept going for a long enough period, we'd see this sort of level off as long as the storm kept going. Here we see a storm that's moving from point A to point B. It's runoff hydrograph versus a storm that's moving from B towards A. Again, maybe it doesn't take up the entire watershed. But you can see if it's moving from B to A, then as time goes on, it's getting closer and closer to the outlet of the watershed, and thus there's a shorter response time between when the precipitation falls and when the flow shows up at point A. And so you see that in here. So various aspects of the hydrograph, and again, here's the same thing with different definitions of what's going on. One thing that we won't do much in this class, but that hydrologists do, is if they're recording the flow rate in a creek, for example, they might get a hydrograph that looks like this after a storm event. If we want to know from that hydrograph that we measured in the creek what the runoff portion was, there's various methods to basically connect point 2 here to point 6 here and figure out this runoff portion up here, and thus what the base flow portion actually was. But we're going to not worry too much about that in this class. So that's just introductory stuff, and now we move on to the rainfall runoff analysis and the unit hydrograph. So this is attempting to introduce the concept of hydrographs that we're going to be working with for a long time, several weeks. Hydrographs in the past, students have regularly said it was one of the more confusing portions of the class. And that's, I think, I've tried to change how I teach this over the years. I think it's always going to be somewhat confusing, but I want to just start off by saying, big picture, what are we really trying to do? We're civil engineers. We're trying to deal with rainfall, runoff, and drainage, flood control kinds of issues. What we want to do is we want to know what sort of flow rate we have when a storm happens. Storms can take on lots of different shapes and sizes. They can be different lengths. They can have different intensities. We know the concept of a storm hyetograph, right, where intensity can be varying at different times in the storm. For any kind of storm event, no matter what the intensity is, what the duration of the storm is, how that hyetograph looks like, we want to go from that kind of a storm event to what does the runoff hydrograph look like from that storm event, so that we can size our infrastructure or analyze our infrastructure accordingly. So this diagram here, we have an input rainfall. We go through our system and our watershed. What does the flow look like coming out of that? To get a little bit more detail, we can look down here and say, all right, here's the basic concept we're going to use. We're going to take our input rainfall, account for abstractions or infiltration. So here's our hyetograph. We already know from previously how we can take that hyetograph and plot it and look at the Horton infiltration. This is the Horton infiltration line. Anything below that line is infiltrated. Anything above that line is going to be surface runoff. So if we take this hyetograph, we subtract all this off, we could get a rainfall excess, which would be our surface runoff. That's this gray shaded part, and plot that versus time. Okay? So we've got our input rainfall, account for infiltration, and we get our rainfall excess hyetograph. Okay? Now, there's this thing called the unit hydrograph, which we're going to talk about shortly, and that's going to be our main tool that we use in order to convert any kind of storm event into our actual runoff hydrograph that we want. Okay? So our unit hydrograph is going to be a really critical tool, and there's a couple ways of doing that. But by using that, we're going to get our actual direct runoff hydrograph. We could add back in our base flow if we have any, and then get our total runoff hydrograph from that. Okay? So let's start talking about what is a unit hydrograph, and then we'll get into how do we use it to kind of make this linkage from the rainfall excess hydrograph to a runoff hydrograph that we want. Okay? So, what is a unit hydrograph? Unit hydrograph is a storm runoff hydrograph generated by a unit, 1 inch or 1 centimeter, of excess precipitation over some drainage area at a constant rate. So we have a storm, that drops, say, 1 inch of precipitation at an even rate, even intensity over some period of time. All right. So let's think about, maybe we picture the Hess Creek watershed. We have 1 inch of precipitation over that watershed over some period of time. What does the runoff at the base of the watershed look like in response to that 1 inch of precipitation? Okay. So once we develop that, what that looks like, then we can use it for other storm volumes, i.e., let's say we have a 5-inch storm instead of a 1-inch storm, we'd be able to use that unit hydrograph in order to predict what that would be. Or things like maybe our unit hydrograph we developed was for a 1-hour storm event. Now we want to apply it to a 3-hour storm event or a 2-day storm event, something like that. So we're going to be able to use it for that. But first, we need that actual unit hydrograph itself. So how do we get it? Well, there's 2 ways. There's getting it from actual data, which we'll talk about first, and then there's getting it from synthetic data, or generating a synthetic unit hydrograph, which we'll do in a subsequent video. Okay, so what are the steps? I'll go through the steps, and then in a separate video, I'll do this example problem down here. So to generate an actual unit hydrograph, we're going to start with a storm hydrograph that I measure. Okay, so one way, the most common way, is to actually measure the flow rate at a certain point for a certain storm. Alternatively, I could measure the rainfall intensity over time, get our storm hyetograph, apply something like phi index or Horton's infiltration methods to get then that rainfall excess hyetograph. But let's assume we're going to start with actual flow data. Okay. I could, if I was in something like Hess Creek that had flow all the time, I could then separate it into parts and get that base flow out. If I'm in a creek or a channel that had no flow before the start of the storm, I wouldn't have to do that. Then third, I'm going to find the total runoff volume as the area under the curve. All right, so if I have the flow rate versus time, I multiply flow rate by time, I just get volume. Total runoff volume over the course of that storm. Then I'm going to divide that total runoff volume by the area of the watershed to calculate the average depth of excess precipitation. So if we look at this equation, we multiply some average excess precipitation by the area of the watershed, I get a volume, right? So if I take the volume I got from my actual hydrograph and divide by the area, I get what precipitation of runoff, what precipitation that results in runoff would I need to have given my area of watershed to generate this kind of volume, the volume I got from my curve. Okay. Once I do that, I'm going to divide every point on the runoff hydrograph I started with by that P average value. This is going to yield a hydrograph of a storm dropping 1 inch of excess precipitation on the entire watershed for the same duration as the original storm. Okay? So, this maybe makes intuitive sense to you, and maybe it doesn't. And if it doesn't, hopefully it will after we do this example problem, which I'm going to post in a separate video. Okay? In this separate example problem, we're going to generate an actual unit hydrograph from this data here. Okay? So now take a minute and start the other video.